So we're going to talk about phase changes and PV diagrams. And I apologize for the background noise. So first, let's talk about what an ideal gas is. Right? So just kind of by definition, an ideal gas is assuming that whatever molecules we have or atoms of the gas, we're assuming they have no size. Right? So size does not affect how we analyze the motion. We also are basically assuming that they don't interact with each other aside from colliding with each other. Kind of a circular definition here is an ideal gas follows the ideal gas law perfectly. Alright, so why is this important? Alright, so when we're dealing with gases, typically if the gases are at higher temperatures, they're going to behave ideally. So they have those properties I just listed. So at lower temperatures, we don't have an ideal relationship because we can't ignore the interaction between molecules because their volumes are much, the volume of the distance between the molecules is much smaller in these states of matter. Right, so when we have a substance changing from, let's say, a gas to a liquid, there's going to be a dramatic decrease in volume, right? And you can see that here in this graph of volume versus temperature. So we have whatever this gas is behaving ideally, where volume is directly proportional to temperature, up to a point of about negative, let's say 190 degrees Celsius, in which it turns into a liquid, and now no longer, the volume is decreases quite a lot. It does not follow this linear relationship any longer. Right? And also it's important to note that volume is never going to have a value of 0. Right? That's because molecules take up size. So that's going to be the case. Alright, so PV diagrams are a diagram of pressure versus volume. They're super important, very fundamental. Pretty much in this entire unit, I would say PV diagrams are definitely going to be on the AP exam. So I'm going to introduce them now, but we're actually going to go into them in a bit more detail later this unit. So if we have a substance that behaves like an ideal gas, we have this relationship, right? That PV is equal to NKT. So let's assume that the number of molecules and the temperature is fixed for whatever amount of gas we're dealing with. This means that PV is constant. I think that's called Boyle's law? It's been a while since I've taken chemistry, but maybe you guys remember. But if we plot PV being constant, what we'll see is we end up with a hyperbola for a pressure-volume graph. Right? That's because these quantities, pressure and volume, are indirectly they're inversely proportional to each other. So we're making a plot of pressure as a function of 1 over V. Right? So we have these hyperbolas here. So like I mentioned before, gases at higher temperatures behave ideally. So when we look at these shapes here, the T's here represent temperature, and T5 is the highest, and it gets smaller and smaller after that. So we have the most kind of hyperbolic shape here, and it looks like T4 is still a hyperbola. But once we get to T3, kind of a cooler temperature, we have this kink in this pressure volume graph. So this is to say that our gas is no longer behaving ideally. Because ideally, if it was an ideal gas, it would have a smooth hyperbola here. So things are getting a little wonky, but that's okay. So as it gets, when we're looking at these different temperatures, these are actually called isotherms. This is an isotherm means we're looking at a gas. In this case, where the gas is changing pressure and volume, but temperature remains the same. Anyway, this graph here is also showing kind of information about the phase of what we have. So we've got a region kind of here in the graph where whatever this gas is, well, it's no longer a gas, it's going to be in the liquid phase. Where over here, it's in its vapor phase. But there's a region of the graph that's known here as a liquid-vapor equilibrium region. So this means that it could be either a liquid or vapor, actually both existing at once. Now just kind of an FYI here, the phase values of our substance here is not typical to be present in a pressure volume graph. But it can, like it is here. Whoops. Alright, so this is the same graph, just zoomed in a bit. There's something known as a critical point. Specifically, it's a critical temperature, though that temperature value here is not present on the graph because we're dealing with pressure and volume. I'll show you a graph later in which it is. But basically, this critical temperature is where the liquid can no longer exist. So there's also a critical pressure, in which is the minimum pressure needed for the liquid to exist at a critical temperature. Alright, so basically, this is information about what phase our substance is in. But we can learn that a little bit more, actually, of something called a phase diagram. This is just a fancy name for a pressure-temperature graph. So here we can see the critical point in a little bit more rigorously, in the sense that we can actually literally read what the temperature value is. In these graphs, it's more kind of obvious what the segments are for the different phases of the substance. Right, so for example, for this substance, if the substance had a temperature of, let's say, 100 degrees Celsius and had a pressure above 1 atm, we see that the substance would be a liquid. Whereas if the temperature was, let's say, 0 degrees Celsius and the pressure was smaller than 1, it's going to be a solid. Now what's interesting is that we have these boundaries in which two phases can exist at once. So for example, if we had a value that existed along this curve here, maybe let's say this point here, that's that when the substance had that value of temperature and that value of pressure, it can be both a liquid and a vapor at once. And there's also a point here known as the triple point, in which it can be in all phases at once. Right, so what does that even look like? Luckily for you, we've got a video. Alright, so this video here is showing the triple point of water. So what we have is a container of water in which it's been, the system is at that exact pressure and temperature needed for all three phases to exist at once. So we've got vapor in the container, we've got liquid and actually chunks of ice here, but you can see here that it's boiling. So we've got the ice turning into a liquid, we've got the liquid boiling into a gas, and vice versa, which is really interesting. Alright, so I have a question for you here. So let's assume we've got this situation going on. Let's assume we're dealing with water here. In particular, according to this phase diagram for water, explain why it's possible for ice to melt when making a snowball. Right? So maybe you've noticed when you make a snowball that you have kind of an outer layer of water going on. Or similarly, why if you're driving over fresh snow, why does that cause a layer of ice to form on top of that snow? Well, the reasoning might be, so we've got a cold temperature, so below 0 degrees Celsius, and if we're looking here, so we've got ice, so in the solid region. Right? Well, if you look at the solid region, if we're at a temperature around here, and we're taking that snow and we're packing it, we're increasing the pressure. So if we move vertically, we see that we can transition from solid to liquid because of that. Right? So this is why, like, especially with the fresh snow in your tires, if you're rolling over fresh snow, it compacts it, it increases the pressure, causing it to turn into liquid, which then eventually freezes into ice. So that's why driving over fresh snow causes a layer of ice. So something I do want to mention is that when we're at a point in which, let's say we're dealing with the boiling point for a liquid, the liquid and gas phases are actually in equilibrium. And I will mention that the combination of temperature pressure has to be just right for this to happen, right? We basically have to lie on the line in our PT graphs, or along that curve, I should say, not a line. But nonetheless, so the rate at which the molecules are evaporating is the same, or I should say, becoming vaporized, is the same rate in which they're condensing. So we can have an equilibrium reach, which actually, so let's suppose we're going to boil some water. So why doesn't, based on what I just said, why does an open pot of water completely boil away? Why does it not just equally condense back into water? Right, so you might make the argument, well, it might be an equilibrium, but, I mean, the key here is we're not dealing with a closed system, right? So the gas surrounding the pot is not just pure water. It's not pure water vapor. There's also air mixed in with it, right? So we're not dealing with a closed system, and also it's not just solely water and water vapor. there's also air being a different gas. Alright, so pretty interesting. A simple consequence, but important nonetheless. Alright, so I won't make you stop to think through this one, but what about if we have, let's say, room temperature water? Okay, so we have a glass of water sitting out. This temperature and pressure corresponds to the liquid region, so then why will the glass of water eventually evaporate? And again, this is because we're in an open system, so the gas around the glass of water is air, not pure water vapor. Right, so therefore the rate of evaporation is going to be much greater than the condensation rate of the water vapor back into, that's in the air now, back into the liquid water. So if we put like a perfect seal in the glass, then this is what this will be the case, is we'll have this equilibrium, and the evaporation and the condensation rates will be the same. Alright, so when we have this gas phase that's below the boiling point, that's when we call this phase a vapor, just to kind of clarify the difference between a vapor and, I guess, gas would not be the right one. But I think that's where I'll end things here, so I hope that was helpful.